Okay, are you ready? Ready? Okay. I don't know how many people online, but it's supposed to.
7:10. We said 7:10.
7:10, yeah. So give it a couple minutes.
Yeah, sorry. Let's see if the thing works. Okay, yeah.
Progress.
Yeah, so it's important to do.
Okay.
Oh, yeah. All right, we're going to start the lecture by Dr. Khan.
Okay. All right. So I'm going to talk about quantum computing with this title for machine learning and a lot of promise, challenge, and realistic outlook. So it's a really very personal journey of this. And over the years, we do something and have different ideas, maybe from the mainstream. That's why I have put on the more realistic outlook. Okay, so you will see some of this. So this is outline and give this short period of time. I have quite a lot to cover. Have you a very quick introduction to ourselves? We do have several members in the lab and working in this direction. So a very quick introduction. And then I will bring you back to the human evolution and the two use and see whether today we are in the age of this quantum age. And then I will mention the analogy analog computing with a problem which related, and then some timelines, then a quick introduction in the Shor's algorithm and growth algorithm and what they are positioned in this whole field development. Then we'll switch gear and to the area which I'm more familiar with is a single cell technology. And because this gave our data points enough to utilize quantum computing, otherwise it won't be possible. I will mention two of the case study in the field I working in single cell biology, which is to use quantum computer to build a gene regulatory network. And also most recently we use quantum annealing to do this feature selection. And you will see some applications to give you some idea that what you can do with your domain of knowledge. And hopefully you have a clear view of what you should learn and whether it's achievable or not. So, okay. In the middle, you can have a quick question. I will have a very quick answer. Otherwise, I just keep going. All right, yeah. So a quick introduction of my lab. So my name is James Cai. So Cai is a Chinese pronunciation. And if you cannot pronounce properly, you can try PSI. So this is the psi, and that's a Greek letter, and very similar. But James Kai, a lot of people call me Kai, is fine. So I'm a professor in vet school. So that's animal science related, so called veterinary integrative bioscience. And I'm also an affiliate member in the ENEC. I think you know ENEC, you are in the ECS. This is computer science engineering. So ENEC is engineering, computing, and engineering. So similar. So my lab is now focused on this intersection of single cell biology and computation using machine learning and also plug-in quantum computers. So I will mention the paper we published. So this is one of the main achievement we did a couple of years ago. So we use a lot of this engineering computing interface with MATLAB, and I teach single cell data analysis for biologists, and a lot of undergraduate students are welcome. If you come, you will learn a lot of this interdisciplinary, how you applied, what's the feature of this very unique feature of the single cell data, and how you can apply machine learning in there. So basically, we are working on the data science, quantum computing, and single cell biology. Okay, so intersection, very unique. You can hardly find any other labs in Texas A&M, for example, working in the same direction here. I want to also mention we have Salim, my postdoc researcher scholar. He's here and help us to support. And we recently published another paper, is quantum annealing in applications for feature selection, and Salim is the first author, and this will be published in the quantum machine learning intelligence, just accepted. So overall, we try this very new area to use quantum to design quantum algorithm to decode gene regulatory networks, and also to use this to predict or model cell phase transition. So cells you can build, change from one state to another, or from one cell type to another, from stem cell become the more matured development cells. So those are the field we are working on. Let's see. Okay, so I bring you back to human evolution. So we common ancestor, the human body, spend thousands or hundreds, maybe hundreds of years in the Stone Age. So if you look at the scale, and we gradually enter this Iron Age. So I separate the human development into different stone tool, iron tools, and different tools. People utilize those tools, which differentiate us from the animals. So what's the age of today? So we will think there, of course, is a silicon age. So you are using neural network, using large language models. That's a silicon. Human being utilize this very effectively, and otherwise they're just sand. So this is a develop of these transistors. Okay, we rely on this highly condensed transistor arrays nowadays to empower of computation of this whole information age. So you know this is Moore's law. So you have the increase of computational power doubled in, I don't know how many months they proposed, but now we achieved to some plateau, and now it could be because of the nano effects when these transistors into nanometer to nanometer levels, we start to have some limitation physically. However, all this information age, all the technologies rely on this very simple binary representations of the information and also operation on the binary operators. Okay, so there's no much difference when you use these computers chips using transistors. And the fundamental rule has no difference from you using this abacus, okay? It all depends on these operations. However, we need to think whether there's other ways we can utilize which physics world provide to us. I give you an example. So we move to an example problem like this called lifeguard problem, mathematical optimization problem. I don't know how many of you knows this lifeguard problem. Okay, the story is like this. You are a lifeguard which surveilling in the beach. So this is this beach, and one of this swimmer is drowning, is dying. So you try to get to this to help her or him. Okay. What you can do, you can run straight to this drowning person. However, because your speed you're running on the beach is different from your speed, the speed you swim in the water. So this blue one is water. So you need to find a particular angle so you can minimize the total amount of the time to reach this person you want to save. So straight line is not the best solution. So you need to calculate the speed you can run on the beach, on the sand, and the speed of your swimming. And you can find the right angle through the optimization procedures. If you know your speed, there's a particular angle you can go to minimize the time you will spend. If you have this problem, I gave you the speed V1 and V2 and the distance and all the parameters. You probably can come up with an optimization procedure, spend some time to find the best solution, which is particular angle you will go. And once you reach the water, you swim towards the people you want to save. Okay, so in this case, you will spend some computational power or time to solve this problem. Okay. We don't need this solution all the time, but if you live in an imaginary world, you need to have a lot of these solutions. You want every day, if you need to compute millions of times of this solution, you want to have different ways to solve this problem rather than use silicon current addition machine to solve this problem, right? So we can use this system to solve a lot of problems. You can do PCA, you can do neural network, boiled down, everything is just addition. Okay, if you know the machine learning, if you know thoroughly enough, you will realize everything we are doing, the vector, database, whatever, you name them, you can always bring it down, brought it down back to addition operation. So we rely on addition a lot. So we naturally require this binary operation all the time, every day. We don't know how many times, but all the time. So in the imaginary world, for example, we need a lot of solution of this particular angle solution. So we can borrow light, okay? So light will give you a nature solution. If you know the light have a speed in the air and light have a speed in this water or other medium, then when you shoot this light to the interface of water and air, it will automatically bend and find the shortest solution for you. So you don't have to do a calculation. So the light will help you to do the calculation all the time. So if you are working in this imaginary world, if every day you need to calculate this to solve the problem hundreds of millions of times, if you want to save time, you probably want to develop a new computer which utilize light to do this computation for you. Okay, other way around, if we know this phenomena, which follow this called the Snell rule, and we have this physical phenomena, can we utilize this phenomena to do computation for us right now? Okay. Can we do generalized all-purpose computation, just use this light wave band through the different medium and find the shortest path for us all the time? So that's the problem the quantum computer computation has a problem. So we have phenomena of this quantum mechanics, and we have manipulation of quantum qubit. How can we utilize this physical phenomena to help us to solve our problem, our real life problem? The same idea. So I hope you get this idea. So we can utilize physical world phenomena to do computation. We just need to find a way to generalize it, can be utilized to help you to solve the problem which addition machine nowadays can help you solve. So in the beginning of the 1980s and 1990s, so Fairman and talk about using quantum computer to solve quantum simulation problem. So his idea is just build that machine to solve particular problem which physics I really want to solve, okay? So gradually we move forward through the development of most recently this quick development over the last couple of years. So we have a way to control the qubit, and people start to realize, can we utilize this superposition and entanglement to help us to solve general problem, everyday problem, okay? But I can tell you it's not very good. It's good for generate random numbers. So that nowadays, not very good for any other stuff. But anyways, people, I believe after the Stone Age, Iron Age, Silicon Age, this could be the next one. Yeah, maybe not. We don't know. So that's a challenge. I wouldn't say it will be, but there are different sectors that drive these applications. People in the chemistry want to do optimization of the molecule position and how these bands are linked. And the financial sectors, they try to predict the stock market change using quantum work, for example. Optimization and the material science want to do the optimization problem to do you have a good solutions by explore many possibilities which cannot be encoded easily using this traditional bits. But I would say it's still very early. So if you think we have early stage of the computer, the classical computer. So nowadays we're probably in the 1940s, 1950s. So if you think of development until today and from this 2025, maybe another 40 years, and if your daughter and can use quantum computer easily, and so think about that, okay? But there's a hype because of those existing algorithms. But this whole infrastructure or understanding the possibilities is built upon these two algorithms, only this very thin foundation. The whole building is built upon these two, okay? I would say 1.5 because Grover algorithm won't give you exponential acceleration for anything. It's only quadratic acceleration. Well, Shor's algorithm is used for to do this prime number factorization. Look at it's developed in 1994. So after so many years, we still only have this single algorithm can show you in theory their quantum advantage over classical computer, nothing else. So the whole foundation is built upon this single algorithm. That's a realistic situation. Okay, so when you heard it in the news, there's quantum machine learning can help you to do all these things. They're not real. Okay, they're not real in theory. They're not real in realistic. We don't have a computer to support any of these applications, which can compete with current computer, which have been developed for over decades, classical computers. So this is in the curve show you this number of digits. The primary you want to do the factorization, and the y-axis the number of operations you will need to do that. If you use the Shor's algorithm, assume you have a perfect quantum computer, you can do it without introduce more operations. Compared to the classical algorithm, you have an exponential increase. This is log scale. Okay, so that's a bigger promise, and the whole quantum computer applications are built upon this assumption. Okay. So Grover algorithm is help you to search for particular states when you encode the information in one of the states after this called the diffusion operators. When iterate a couple of times, it will show up. So people use this as a search for the unstructured data sets. So if you have a dictionary, there's only one keyword you want to search against and found out, that algorithm will set it up. But it's a very unique setup. You need to that a lot of conditions. Okay, so a lot of conditions. So it's not a very generalized algorithm. You can say, okay, I want to search particular key password in the random generator. It's not okay. Anyways, we are here because we are interested in those things. But there are some foundation you need if you really want to get deep into there. So you probably have some basic touch on those concepts like linear algebra, probability theory, and the complex numbers in your high school, but you need to polish it, okay? Because without those, when you see the equations, you got lost and confused, panicked, and then you don't have a further ability to track the change of the quantum states, because you need this tensor multiplications, and then you need rotation matrix. And if you don't have those ideas, well, very quickly, when you have several layers of this quantum operations, you will get lost. Okay, so Grover and Peter Shor and those professors, they have a very strong mathematics background, and everything put together, and by chance they get this idea. Okay, so interdisciplinary research and also strong mathematical background will help you. Okay, so our goal here is to, as a applications development, we want to develop particular application in our domain knowledge through deep understanding of what those algorithms and how the qubits and the quantum computing facilities will help us to do. So I show you this applications, what we can translate every day we're working on in the bioinformatics, how we think, link those dots and see, okay, there could be applications. So I'm going to introduce two case studies. Salim, are you going to introduce the second one? The second one will be the one you just published, quantum annealing. Yeah, okay. So I will discuss the first one, and Salim Romero, he's a first author of that paper, so he know much better than that even. Oh, okay. So we a couple of years ago, and we have this quick development of single cell technology. So we think there's two technology revolutions, very major ones. When they intersect, there's something should happen, but you need to know both. Okay, I gave you some idea what this single cell technology is about. I assume you are computational science background. What's your background, by the way? Most engineering background, computer science.
Yeah.
Okay. Yeah. Yeah. So anyone from biology, medical related? Yeah. Heard about this single cell stuff? Okay. Yeah. Yeah. So the people try to understand the biology because the cells are the fundamental unit of the biology organism. So if you can study individual cells, get information from population of cells, and that will be very useful how this a lot of biological cellular level phenomena happen. Start from 2009, so it's not a long time ago, until 2017, there's gradual increase of the numbers of cells for each experiment we can get information from. Again, this is log scale. So up to 2017, there's huge breakthrough. This California company called 10x Genomics introduced this device. This device allows you to capture individual cells with a droplet. It's oil droplet. If you can see this black cell, the black dot is the cell, and it moves through this channel, and the droplet will capture it. And once you capture this droplet, some of droplet will be empty, then it will throw away. But this is the cell inside the droplet. If you look at this cell is in here, and the droplet is there, and there the DNA barcode system will help you to label the cell with a unique signature with ACGTs. So each individual cells will be labeled uniquely, and later when we sequence them, and we will see, okay, this cell will express this particular genes, another cell express different set of genes. So with that technology, we can first get the tissue from animal or human tissues, dissociate them into solutions so they have a chance to be captured individually. Then we have a cell barcoding system, and at the end, we will get a matrix like this. So this matrix will contain information of thousands of cells and their expression in thousands of genes, okay? So you can think about this very huge Excel spreadsheet with many rows, many columns, and their count numbers. The 3 means this cell expresses this gene 3 copies, okay, approximately. So with this information, we can get a kind of a landscape of many cells and many genes and their expression level. So this just show this way, this heat map in the different ways. So why we need those? We need this information because we want to see whether there are different profiles of the cell, compare healthy cells against cells from diseased states. So this is a landscape you can build upon understanding this, each cell's expression profile. So we want to know the transition, okay, from a healthy to disease. We also want to know whether there's a perturbation we can push the cell population from this particular states back to the healthy states. So if we can solve this problem, and a lot of this disease-related problem can be solved. So this cell type specific. One way we can solve this is to build gene regulatory network. Okay, so we will look at this particular landscape and look at pairwise genes. If I found this gene against that gene, if they are positively correlated, I see, okay, these two genes in the population of cells, they always upregulation or downregulation at the same time. So we can build a link between these two genes. If I have three genes, I can build a link again. So at the end, I make a big network. So we want to build a big network with a correlation or regression method, which is commonly used. We also have some called a Boolean network-based method. So I will quickly go through this Boolean network method. So you get this gene expression matrix from a single cell experiments. As I said, you have a lot of genes, a lot of cells, and their numbers. You can binarize them into the 0, 1s. Okay, it's better to be binarized data, and we know it's not lost many features. And also it's very useful later for the quantum computer, because the quantum computer will be probabilistic. It's always generate 1, 0 at the end when you measure the quantum circuits. So there's a particular link between that. So once we have a binarized matrix, so this matrix will have a similar feature as your raw data, okay? And from this binarized matrix, we can classify cells into different bins. If you look at this particular bin, this bin looks high because a lot of cells have a feature as 1, 1, 1, 1. One indicates that the gene is upregulated or active in that cell. And if you have all the genes you under consideration are active, so you have that cell in this bin. And if you have a cell which located in this all 0 bins, means that the cell is not doing anything. All the genes under consideration are shut down already. So this histogram tell you as a population of cells, say 1 million cells, I have 100 cells in this particular states and 2,000 cells in the all 1 states. So this 1 and the 0s indicate particular gene in your sample is active or inactive. So once you have this cell activation state histogram, you can build a network between transition from one state to another. So this is the whole idea of the Boolean network. You guys are computer science, you know the Boolean network probably already. So you transcend from one state to another. So those links are just one difference. Okay, you can jump from 1, 1, 1 to all 0 states through this pathway. Anyways, so this Boolean network idea is to help you from transition probability, cell states, and then you can start to infer which gene is regulate which other genes. So that's the foundation for the application for the quantum algorithm. It's based on the Boolean network. Okay. So the problem with the Boolean network is it's hard to scale up. Once you have a lot of 200 genes, you will have a 2 times 2 power to 200 different states. So this search space gets really big. So we are going to build that into the quantum computer for using this way, I show you. So first, our idea is to use each qubit to represent a single gene, okay? 1 gene, 1 qubit. If you study 5 genes, then you need 5 qubits in a row. So qubit, you know, you can use this block sphere to represent its states when this spin is on the point to the up. This indicate 0 states. So if you measure it and you get a 1, you measure, say, 100 times, you get 100 times 1. So this is a histogram or probability of your measurement. And if you turn this spin to downwards, and then when you measure it, you can indicate this is a qubit is in the 1 state. And you measure it 100 times, in theory, you should have 100% 1 state. Well, when you turn this qubit into the hyperposition states using hard mother gate, and this just like a coin which is flipping in the air, and then when you measure it, you have 50% to be 0, 50% to be 1. So when you set up a qubit in superposition, and we will use this to represent this particular gene is represented for is in the either active or inactive states. Okay, so what that means, if you have 1 million cells, if you measure this particular gene states, half of the cells will have this gene activated. Half of this 1 million cell will have this gene inactivated. Okay, so this is a representative of the active of the cells of this particular gene in the population of cell through this probability distribution. You will see if I have a cell and we can detect in a real population of cell 70% active, 30% inactive. How can we represent in the qubit? So in this case, we can rotate this qubit into a particular angle rather than the hard mother gate, which is a fully the superposition, but it is like half superposition. Okay, in this case, if you measure that, you may get 70% 0, 30% 1. You can change the angle of your setup. Okay, so I'm detach you away from the physical experiments. You can use a microwave, you can use a laser to control electron or other ion, and there are people using optical system to set up their qubit. But this is just information process. We just see we have this perfect qubit, and we can rotate and change the angle to let the qubit to, once we measure it, we have a 30% of 0, 30% of 1. So this will represent a gene which actively active in the population of cell in that particular percentage. Okay, now let's consider 2 genes at the same time. Okay, so as I said, if you put this gene 1 into superposition, when you measure it, you have 50% 1, 50% 0. If you put the same condition for the second gene and consider 2 genes at the same time, just like you consider 2 genes in the population, and you found some cells have no expression of these 2 genes, all zeros. Some cells have both genes expressed. Some have a 0, 1, some have a 1, 0. So this is the condition you have simulation for those purely random. So in that case, you should see in the population of the cell, you have 25% of each of the states. Okay, 1, 1, 0, 1, 1, 0, 0. Okay, in this case. So this is a 2 genes simulation. If you have 3 genes, you will have how many? 8 states. Okay. You have 4 genes, you have 16 states. 0, 0, 0, 0, 1, 1, 1, 1, and everything in between. So if you have a real experiment from your population, from your human cells, for example, you can have the distribution looks like this, and you can build quantum circuits to set up your qubits to simulate the probability distribution of the states of all your populations. Okay, now this everything is independent. So this is unlinked with that. That's why you have 25% each. However, if you use the so-called control gate, and 1 state of 1 qubit will have impact on another qubit. This is called controlled RY gates. You can introduce entanglement between circuits. So this will indicate once this gene is switched on, and you will change that gene into, give that particular gene into another angle to change that activation of another genes. So you can build this RY gate between qubits to simulate this interaction between genes. So that's all the idea. We had this idea and tried using MATLAB had this quantum computer toolbox to help you. And if you are familiar with IBM, the system, this Qiskit, and you can have this interface to help you to design this like a 3-qubit and the RY gate to change the rotation. And then here's a Hartman gate. Then there's CX, okay, to control the NOT gates to do the entanglement. And then you can achieve some of this distribution of different states. Okay, 3 qubits, you have 8 states. Once you have this set up, this 111 is in this particular frequency. So what you have to do is just set up this circuit and entangle them and try let this histogram match your observation from real biological single-cell data analysis experiments. So that's what we did, and get the real data and binarize them and set up this histogram and try to build the quantum circuits by introducing angles and controlled angles and to try to let this histogram match the simulation. Okay, so that's from a real experiment, and this from quantum circuit simulation. Once they matched, we know, okay, this setup maybe is some kind of reflection of the real network between genes in the cell population. And then we will care more about the parameters here, okay? So which one is regulated which in that setup. So that's the idea. In the middle, we have to fit this histogram. So this looks like this, and how much difference. This is through classical computer optimization. So there are many optimizers you can use. So we put it in the real applications. This is a B cell and R1. So the particular regulatory network, we involve this genes. So after optimization, you see this real observed and the orange one simulated from the quantum computers. They matched very well, and we see, okay, we read out those parameters and see, okay, this is positive, this is negative, and start to build the real network. So why we do this? One argument is in the classical computer, you do this correlation. So those correlation or regression is always from pair 2 genes each time. So you look at the gene 1, gene 2, you do the regression or correlation, but you cannot have a control for the overall at the same time. Well, quantum computer allow you to do this superposition, everything in the air. So until you measure it. So this gave you a slightly different thinking. So the whole idea is if you know how to use it and try to build into your problem, maybe you get a different solution. Just like I showed you, if you know the light will bend and go the shortest path, can you use the shortest path to solve the real world problem if you map that solution or way of solution to your problem? So that's how to map this. This is the hard part. Okay, so that's require you to understand your domain knowledge and how the quantum computer work. Okay, so next part I gave to Salim, and Dr. Salim will help you to understand quantum annealing based QUBO. QUBO is stand for quadratic unconstrained binary optimization. Okay.
Will I step in here?
You can, if you want to stand there, yeah, you can.
I can be here.
Okay.
Right. Well, this is Celine Romero. Thank you for having me today here. I wasn't expecting it, so glad to be here. Um, and what we did in this work, what's the next image? Oh, yeah.
Salim, you come here because there
Yeah.
are Zoom people, maybe
Oh, yeah.
they want to,
Great.
they
In
need
here?
to- yes, I'm here,
All right.
there, yeah.
All right. Well, in this work, we had some fun. And I want to just, before explaining this picture, to state what the quantum annealing is. It's another way to do quantum computing. And this is a little bit different than the gate-based. It's similar in behavior, but it's differently how you reframe the question. So what we did here is try to do quantum annealing. That is, you have an initial state, and then you anneal that little by little. You start tweaking it little by little, and then you start reshaping that to the solution you want. So that's the whole purpose of quantum annealing. It's still driven by quantum device, and it also has a quantum behavior entanglement and everything. But the difference is that you reframe the question differently. So this picture is to how we think the problem. So we originally thought that, hey, what if we have a gene regulatory network? And this is just an example. It's not related exactly to the work. But what if we have a gene regulatory network? What we see with correlation-based methods, we see just one static value. And it's static in one way. It can be just one single value that even have a direction. And what we don't have in the framework or picture of gene regulatory network, it's like we see this snapshot, but in reality, what we have is that it's revolving and it's evolving according to time. So we're having just a little snapshot that we are not capturing properly, and that's just part of the picture. So the quantum annealing, it's gonna try to look for the solution, exploring kind of these dynamics, depending how we reframe that. Again, in this problem, what we propose is basically having, again, the cone matrix, which contains genes and cells. And what we try to take is a predictor. And this predictor takes into account the cell states. In this case, we want to know what makes it different from healthy cells from disease cells. And let me see what's in here. Right, and then we want to dissect what's in the states in the time series, right? So this is just, again, this is the broad picture, but can be a little different. Again, we have now that the cells are not just in that fraction or snapshot we have. That's one problem in the single cell, is that when you sequence, you get every single cell in the current state, and they are trying to differentiate. Some are in the middle, some are just bursting. So we have this dynamics, but in a static manner. And still, we want to use that predictor evolving of the cell state to predict. And what we propose here, it's looking at the cell differentiation for this data set, which was differentiating from embryonic stem cells to endothelial cells. This is a known differentiation, but people usually don't know what are the crucial gene set that are making the differentiation into that state. And that's part of our question in this work. And in this, we had this selection with lasso, which is a classical method. And here we demonstrated that it's a classical method and don't care much about what happens in the middle. So you have only a static, monotonically increasing or decreasing expression across time. Here we have the pseudo time, and the expression is standardized in the vertical, and we have only the expression going from one initial point to one final point. But what we demonstrated in this work is that it can be a little bit different. Can be this in the middle here, where we have something that is going to that cell state, but then is driving back. And that it's potentially a crucial gene in cell fate. And again, this was all based into quantum computing, and we utilized the quantum annealing. We utilized a D-wave system in this work, where we reframe the question, we build the matrix, and we ask, tell me from this matrix of gene correlations, what is the most important configuration for the cell state. And in this case, the cell state was the differentiation from one cell type to the other, but can be different cell states. For example, let's say we find a way to predict cancer states of cells. If we do such a beauty, we can predict which genes are related to that transition. And here in this work, what we utilize it again is the cone matrix and the predictor. The predictor here, we utilize it, the pseudotime evolution of the cells to predict the state, the final state of that. And we did the mutual information within each gene to fill up this matrix to get the redundancy. And the predictor versus all the cone matrix to get the importance. And this is very interesting because the importance of every feature or gene correlated to the cone matrix and the state is the ones we want, but we don't want correlated genes and also coming out as part of the set. We want master regulators. So the whole purpose of getting the redundancy matrix here is having this score of how much one gene interact with another. So we have that score that we don't get repeated genes that have similar functionality. And that's for getting this Q matrix. And then we submit that to the quantum annealer and get the feature selection, which is a binary predictor, telling us this gene is important for your cell state and this other is not for your current cell state or evolution. And we did this work and we got a lot of fun. Interestingly, we got it published like 1 week ago, right? Got this good news, and that's published in Quantum Machine Intelligence. It's a very interesting journal.
It took 1 year for the review.
Oh, God.
For the review.
Right.
Take a long time to publish.
Right. Right. And the first one of the reviews was one of the review comment is like, you have that cell state. Give me another example. The other example we utilized it was drug resistance in cancer context. And we demonstrated that the gene selection we got are explicitly in the paper we took the data set. And that's already demonstrating very, very powerful predicting power to discover therapy to target genes, which is what people look for all the time. And here we did not only compare Cubo versus Lasso, we did some other more like random forest regression, but the most straightforward comparison was Cubo versus Lasso, in where we demonstrated some key drivers in this study, the cell differentiation from that cell type to the other cell type. We demonstrated these 3 genes, APLN, ID1. Those are very crucial genes differentiators for this embryonic differentiation. And interestingly, this part of these genes were the ones that are resisting. So that's already telling us that could be potentially not only one fate, but multi-phased, multi-state differentiation can be branching out even within the same cell type. That's what we wanted to demonstrate with this. And here, the non-linear genes we found that definitely were omitted by Lasso, where this interesting IGF-BP5, for example, is one very crucial gene in the differentiation. And we demonstrated here that it rolls back, and that's overlooked already. And all these genes, for example, this BIM even looks like a circadian rhythm pattern. So it's going and resisting to evolve, and then it finally just ends up in that final state. So that's the whole story in this gene set that is completely nonlinear. And what we demonstrated here is that after doing the enrichment analysis, we found that, for example, these 3 genes here are completely related to the specific cell type evolution, differentiation we were looking at, which was related to smooth muscle proliferation. That's indicating that is already getting from one fate to another. And also tight junction, for example, was coming out. So this is basically demonstrating that the genes that we are getting are not only unique, but also are the most important, and we're targeting to the master regulators all the time. Sorry, this is what, sir?
Okay, yeah, so the.
That's
Thank you,
it, right?
Salim.
Thank you, Salim.
Yeah.
Yeah. So very quickly before we finish, so this is a application in biomedical research, and some government efforts want to put in, and so they start to release this kind of challenging questions, and then we have some internal future directions, try to see the difference in the network, and Salim is working on, and we have a quantum circuits designed for simulation, not only gene expression level, but also epigenetic states. And I want to thank our organizer, and Samuel is in the chat, and then other members of this organization. Okay, thank you very much for your time. I think I have some quick questions. All good. No problem.
Thank you so much, Dr. Kai.
No problem. My pleasure. Bye, Samuel.
Right.
Thank you.